Hey everybody, I wanted to respond to some questions about assignment 40, what affects the speed of a ball at the bottom of a ramp. Question 3, which is really the first question where you're setting up all of the equipment on your own and needing to record your own videos and analyze your own videos to be able to get the information. And that really is the next step in solving the problem. The reason I recorded the videos for the earlier two sections is just to expedite your process, to move it along a little bit faster. So I can see where some of you are coming to this moment and going, he's asking us to do what? So let me clarify for just a moment. One of the challenges I think that we have in the American educational system is that we often do too much for our students and don't let them wrestle with things. And so in this video, I'm going to give you some tips and tricks as to how to solve the problem. But I'm going to encourage you, if you're willing, to just stop the video right now and see if you can sort out the problem for yourself, right? It is worth your time and you will learn more by doing that. And so if that's you right now, you're like, yeah, I'm willing to take that on. Just stop the video right now and go forth and see what you can come up with. If you need to come back and get the remainder of the video, do so. For those folks that need a little bit of extra help, some tips and tricks, I'm going to get to those right now. And then as we move forward, I'll go ahead and solve more and more of it, but I'm not going to solve all of it. So please stop the video at what point you feel comfortable doing this on your own. It is really important to know that education is boring if you just do what teachers tell you to do. And if you solve problems on your own, you will find them more satisfying and more interesting and more long lasting than you ever could by doing just by filling in the blanks of kind of what teachers sit in. So at this point, there are some blanks to fill in, and you can see them just there on the lower left, or whichever direction that is for me. And that's true, but in order to get to those blanks, there's some work that you have to do on your own. So here's some tips and tricks. First, you're going to be building a ramp using a meter stick or two, as well as a long plank that you found on the side of the classroom and a ball bearing to be able to roll down. I encourage you to go ahead and use 2 meter sticks actually to sort this out, where you place both meter sticks on the plank distance apart from each other such that the ball bearing can roll down in the gap between the 2 meter sticks. And you saw that in my video from earlier. So we've got meter sticks to work from, we've got ball bearings, and we've got ramps. And you'll need to prop those up using something like books or bags or anything that can kind of turn this into a ramp that you can measure an angle from. Your goal is to create 3 different ramp angles. And those ramp angles are here at 2.2 degrees, 4.4 degrees, and 6.6 degrees. And our goal is to start the ball bearing from the same height on the table every time. And that height from the table, right, is 0.01 meters, which is 1 centimeter from the table every time. So the question becomes, how far up the ramp do I need to put the ball bearing such that it is 1 centimeter off of the table? And secondly, how can I even make a ramp that it is at the correct angle of 2.2 degrees? So in order to get the correct angle of 2.2 degrees, that's the easy part. Or dare I say, the stuff that you've been working on lately. So what I'm going to do is I'm going to put a line down here to represent my ramp. This is the meter stick. So this is 1 meter long, and I'm going to be propping it up on the floor or on a table or something that is horizontal. And so this is the table, let's say. And I want to make an angle here of 2.2 degrees. Well, to do that, I find the easiest way is to go ahead and come to the end of the meter stick here and make sure that it is a certain distance from the table down below. And the distance needs to be calculated using this right triangle, which we've now created. And we've done this. So the height off of the table here, which I'm going to call h, right, is such that I've got 1 meter for my hypotenuse, right? This is my hypotenuse. And my height is the thing I don't know, and that's going to be opposite my angle over here. And so now I just need to plug in this equation here, which is the sine, because I've got opposite over hypotenuse, right, of my angle, which is 2.2 degrees, is equal to my opposite, which is my h, which I don't know, divided by my hypotenuse, which I do know, which is 1 meter. Now, if I'm solving for h, I just need to multiply by 1 meter on both sides. So I multiply by 1 meter on this side, I multiply by 1 meter on that side, and that means I'm going to end up with just the sine of 2.2. And if I grab my handy calculator here to do that, I take the sine of 2.2, which gives me this. So h equals 0.038 meters. That looks like an N. So h equals 0.038 meters, right? Well, how high is that? That is a distance of 3.8 meters from the table itself. So my distance that I want this to be is 3.8 centimeters from the table in order to get my 2.2 degrees. If I need this to be 4.4 degrees, then I just replace the 2.2 here with 4.4. Or if I need it to be 6.6, I replace it with 6.6, and so on. That allows me to create my triangle. So now I have this triangle that is the correct angle. So next I need to go ahead and figure out, how do I make it so that I'm dropping my marble or ball bearing at the correct position every time? So to do that, I'm going to go ahead and form another triangle here. But this time around, I'm going to say, all right, I need this to be 0.01 meters from here to the table, right? So I need a distance here of 0.01 so that I can put the ball bearing at this position so that it can then roll down the ramp and I can check the speed of it right here. Same deal. I now have my 2.2 degrees there, and what I'm looking for is I'm looking for this distance here, and this distance here is the amount of distance that I'm going to allow to roll down the ramp, and we're going to call that d. So to solve for d, we're still dealing with the sine. So now this is the sine of 2.2 degrees is now equal to my opposite, but my opposite is 0.01 meters. And now I'm dividing by d because that's the part that I don't actually know. So if I'm solving for d, I need to multiply by d on both sides, right? That means it cancels over here. But now I've got d times the sine of 2.2, so I now need to divide by the sine of 2.2. So I'm going to divide by the sine of 2.2, which means that it's going to cancel over here, and I'm going to divide by the sine of 2.2 over here. So d is equal to 0.01 divided by, that's meters, the sine of 2.2 degrees. Great. So what do I get? All right, so I'm grabbing my handy dandy calculator again to make this work, and I get 0.01 divided by the sine of 2.2. And the distance that I need to put the ball up the ramp is 0.26 meters. 0.26 meters, and 0.26 meters is 26 centimeters. So I need to place the ball on the ramp here so that it is 26 centimeters from where I'm going to be checking the speed measurement. Remember that this part up here at the top, the starting height and the distance, do not play into the speed measurement, which is down here, right? So this distance rolled down the ramp is going to be 26 centimeters, right? Or 0.26 meters. So 0.26 meters. And my height that I'm going from the table is 0.01 meters. And I'm all set. So I'm ready to go. I'm going to roll this exact same thing again, but the next time round, I need to go ahead and get it at 4.4 degrees, which means that I need to figure out a 4.4 degree angle. So you need to figure out what the height will be at 4.4. And then you need to figure out what the distance up the ramp is in order to make sure that you have a height from the table at 0.01 meters. Because that's the goal here, is to keep the same height from the table, even though our angles are changing. Fair enough. That's a lot of information. I'm hoping that's enough to be able to sort things out, and we'll go from there. So if you have got all of the information you need, go forth and plunder. Figure out how this whole thing goes for yourself. For those people that are still stuck, you're welcome to keep watching for just a moment. I don't have the equipment here to be able to do the whole thing for you, but I did solve the first one of these three. What I need to do for these parts down here, right, is I need to do the same thing that I did on the ones from before. I need to determine some sort of change in position. I'm going to suggest that you use just the last little tiny bit here on the ramp as you film it, and that I suggest that you film it in high speed if you can. That'll allow you to be able to count frames a little bit easier, but recognize you need to divide by the frame rate to be able to figure out the time. So in this case here, my distance at the end of the ramp might be 1 centimeter that I'm filming from. And then my change in time might be the amount of frames that it takes to go 1 centimeter on this one. And then my speed is just this 1 centimeter divided by the time in number of frames divided by the frame rate as we go. That's going to give you your speed right here. So how do you do the next parts? Well, the next parts, as we're looking at it, we started with a 2.2 degree angle. So let's see what we could do if it's not 2.2, but rather 4.4. How do we solve that instead? Well, if we're doing it for a different angle instead, like 4.4, you still have the same principle here that you did before. And that principle is that I will have 4.4 degrees now. Oops. And that's a 4, even though, man, this erases everything. There we go. So to get this angle out here, as long as you're using the entire 1 meter, we did this once before. This is now the sine of 4.4 degrees is equal to, again, this is my y value here, or an h value, is equal to h divided by 1. And that's the same as just taking the sine of 44 equals h. So whatever the sine of the angle is what it's going to be at 1 meter. So that should be easy enough. To get this starting height for each one of these, same idea as before. We still want to have this distance here of 0.01 centimeters or meters, right? And so we're going to do the same thing that we did before, where this time it's going to be the sine of 4.4 degrees is equal to my 0.01 meters divided by my value d, and I'll solve for d on that, and it's going to give you a distance that you're going to roll down the ramp. And you do the same thing again for the 6.6. So let me go ahead and do that here. So this essentially is 0.01 divided by the sine of 4.4. And now my new height or distance that I want to roll down the ramp is not 26 centimeters, but rather 13 centimeters, right? So this is going to be 13 centimeters that you want it to roll down the ramp. So 13 centimeters when you're at a height with a 4.4 degree angle. Keep in mind that that's also written as 0.0 or 0.13 meters. And over here, we're going to do the same thing, only not 4.4, but 6.6. And now the distance that I want it to roll down the ramp is 8.7 centimeters down the ramp. So this distance that I let it go with, man, everything's disappearing. Can I? Oh, no, not quite. I'll just right over the top of it as 6.6 degrees is 8.7 centimeters, right? Or another way to write that here is 0.087 meters. All right, I hope that's enough to get you started and get you deep into the work. You're still calculating the speed in the exact same way I did the other video, but now you're building your own ramp. So good luck. And there's a graphing portion on assignment number 41. If we need more time on this on Monday to be able to finish your graphs, I'll give it to you, and hopefully I'll be back in action at that point. I still have COVID. I'm still testing positive for COVID, but my symptoms are relatively mild. It's just a requirement of the quarantine for making this happen. So, all right, take care, everybody. Bye.